So hello everyone, I'm Liana. I'm an ML engineer in Podcastle, and today I'm going to introduce you the advancements of generative AI in audio processing field. Mainly we will focus about achieving studio quality speech with generative AI, where I will show how the advancements of this field can make your spoken content into professional standards. So before diving into methods and solutions, let's just define the problem. The goal of speech enhancement is to create an audio processing system that transforms noisy or degraded speech into studio quality audio without perceptible artifacts. So given a diverse data set of paired examples, noisy and clean audio, we need to learn a highly sophisticated function f, which will convert the noisy signal x into a clean, high-quality signal y without introducing perceptible artifacts. So where this kind of system can have a significant impact, for example, in voice calls, it can improve the quality of the audio, which will contribute to more enhanced communication between the participants. The same can be applied for video conferencing, virtual meetings, and any type of audio that is recorded and contains speech. It also can play a crucial role in assistive devices for people who have hearing impairments by amplifying and reducing background noise. So what are Podcastle use cases? Podcastle enables its users to record audio in any environment and make sure that it is recorded in a professional studio without needing the proper equipment and the staff for recording your audio in a professional studio. It applies this system before voice cloning to make sure that the cloned voice sounds natural and refined. And the third one is an internal use case, which helps to remove the background music from the audio to enhance the ASR accuracy, which makes the system more precise. Seeing the significant impact of the system, the path to studio quality speech is not straightforward. It is fraught with challenges which need to be handled carefully. The first one is the noise variability. Like the real world introduces a diverse set of noises, wind, traffic, some background chatter, which differ by their frequency content with their intensity. And the system needs to be robust about different kinds of noises that we have in real life. The second one is the complexity of audio signals. The audio signals are very complex. They differ by their pitch, by their frequency, by their dynamic content. So it's really difficult to have a system that handles all these kinds of audios in a right manner. The third challenge is generalization. The system needs to be robust about the unseen conditions because the model cannot see all the noises that we have in the real world. It's a really difficult challenge to handle to handle all the conditions that we have that the model haven't seen. The fourth one is the scarcity of the clean data. Having paired examples of noisy and clean speech is a very difficult challenge, and I will introduce later in my slides how people are doing it. And there is only one data set, and having this kind of problem, we need to think about the ways how we can obtain a large data set for training. And the fifth one is artifact minimization. It's a huge problem to have a system which will reduce the background noise without introducing perceptible artifacts to the speech, without distorting the natural characteristics of the speech. Before examining our approach, let's see what previous research has done in this field. The first methods are traditional signal processing methods like linear filtering, weighted linear prediction error, non-negative matrix factorization. But these methods have their problems, like they assume that the noise is stationary. For the second one, the weighted function needs to be selected carefully. And the third one is highly computationally heavy. And these approaches are out of date because they also introduce some unnatural artifacts, which are then people tried to solve by deep learning methods. The second family of the methods, as I said, is deep learning methods, which do this task by via mapping from input to target or mask over input. Here I mentioned some papers which have good results, in terms of the quality in the research area. So voice fixer is a method that does this by mapping from input to target. But these methods have a disadvantage because they require inverse short Fourier transform or a vocoder to get the final waveform, and without having the phase information of the audio, we have unnatural artifacts in this kind of approaches. The third approach is the same like deep learning methods, but they also predict the phase information of the audio. But these methods also have their disadvantages in a way that small errors in a phase can result like unnatural characteristics of the audio, some artifacts. So these methods are also not producing great results. The fourth one is waveform-based methods like Hi-Fi Gun or Hi-Fi Gun 2, which are models from Adobe. They have impressive results, but they also have some audible artifacts in their final results. And the fifth approach is like diffusion-based methods, which gain traction a lot in the recent times. And they are highly effective, but they are computationally heavy. So we haven't approached them and haven't trained these kind of models yet. And I don't know you will get this presentation or not, but in the last point I mentioned some repo, which is a timeline of the speech enhancement evolution and all the methods that are in this field. So let's speak about Hi-Fi Gun, which is a model that have impressive results. It works on a 16 kilohertz of audio data, consists of the generator, which is a WaveNet architecture. Then it also has some convolutional blocks, which consist the postnet module. And then after that, we get the final waveform. And on the final waveform, 3 waveform discriminators were applied and 1 frequency discriminator to resolve the artifacts from the generator. These two losses, these two L2 losses are the main, these two L2 losses are the main contributor to this system, but the L2 losses have their disadvantages in a way that they blur the spectrogram, and when we have a blurred spectrogram, we have aperiodicity and ghosting effect in the spectrogram, which also produces unnatural artifacts. Like a periodicity is the smoothed harmonic structure of the spectrogram, and the ghosting effect is like that the fundamental frequency and its harmonics are not aligned with the clean version of the waveform. So this model uses these two L2 losses and also the adversarial training losses, generator and discriminator losses, and also feature matching losses. Here we have also the postnet here plays a crucial role in a way that generator produces some audio and postnet tries to like refine the coarse version that is generated from the WaveNet model. The next approach that I want to speak about, which is the best, which is one of the best ones in the field, is a Storm paper, which introduces a different approach. It is based on the diffusion processes. Here we have an audio sample like X, and from that we want to, on that we do a forward diffusion process where we get a like standard normal distribution, which is a tractable prior distribution, and neural network learns to reverse this process. But as I mentioned, these processes are very computationally heavy, so they approach this problem in another way. They thought about like combining the predictive and diffusion-based approaches together, where we have a predictor model, which is trained on L2 loss. And after that, they apply the diffusion process on that predictor result. And in that way, they like had great results with minimal diffusion steps. So this is from the current results that are impressive and also not computationally heavy. Also, in that way, they refined the artifacts that we have from the predictive models. As I said, that predictive models have had a problem which is known to regression to the mean, and they cannot capture the fine-grained details of the image. So combining this approach, approaches results in a great performance. So what are the existing data sets for speech enhancement? The first one is DAPS dataset. It is well-constructed dataset for speech enhancement especially. It is 56 hours, 20 speakers. It is recorded in 12 real-world environments, where each speaker contributes to the data set in 14 minutes. It is the only data set that we have for the training, but it's like too little. It's 56 hours, so yeah. And I can also describe how this process is done to constructing a speech enhancement data set. Because we cannot have the clean and noisy aligned versions of the audios, they had only the clean version, and then they put some loudspeaker on a table in the height of a seated person, and then they recorded the clean version of the audio, which sounds from the loudspeaker in different devices like iPhone, iPad. So this is a challenging process to construct this kind of data set. The second is the noises data set. We have a public data set, which is the demand data set. It is 22 hours. We have short noises, which is 2 seconds in duration, which we scraped from the internet, and long noises, which is 87 hours. And also we have scrape noises, which are known as free sound noises. It's about 500 hours. For the room impulse response dataset, we used MIT acoustic reverberation dataset, which is like 271 impulse responses from 301 places. Besides that, we also used pyromacoustics package, which allows us to simulate real life reverberations, and where we can define the room parameters, the materials of the walls, the positions of the sound sources, microphones. So it's a great package to use for getting simulated acoustic environments. So having known that it is crucial to have a large data set, how we can obtain a data set for a training. We collected and scraped podcast and audiobook data from different sources. The sources are in a huge amount, but the quality varies a lot. So we need to have some classification model which will classify the data set into 3 labels as we defined it for our system: HD, clean, and rejected. HD is the class that we wanted. It contains minimal noise and not artifacts. Clean can have some kind of reverberation, a little. And rejected is the one that can contain background noise and different distortions which are not usable for our system. After annotation, you need to adapt some classification model to get the data set that we wanted. This classification, there are a lot of classification models which are trained on audio set data set, like AST or WAV2VEC, or some CNN-based approaches. So you can adapt the model on the dataset to get the refined version of the dataset. After that, after collecting the dataset, you need to train a speech enhancement model with a huge amount of dataset. After all these kinds of processes, we gathered 22,000 hours of data, like the HD class, which is the 9% of the total scrape data, and it is mainly in English. So having a diverse data set which can simulate the different environments of the world, we need to do some data augmentation. The first family of the augmentations are band pass filters, where we can apply low pass filters, high pass filters, which can isolate some frequencies and will help the model to be precise on this type of audios. The second one is equalization. Equalization balances the frequencies of the audio. The third one is reverberation and delay, which will simulate the acoustic environments that we can have in different places. The fourth one is synthetic noise, which simulates like the interference of the noise in our audio. And the fifth one is loudness dynamics, where it will help the model like to handle the audios that have different volumes, high, low. All these type of augmentations, their grouping and their weighting are derived from a universal speech enhancement paper, where they mentioned the groupings of these augmentations and also the weights for the training. So before diving into our model architecture, let's first know what is a reassigned spectrogram, which we used in our model and which impacted a lot on the results. A reassigned spectrogram enhances time frequency analysis with better localization. useful for complex signals with overlapping components. So here we have a traditional spectrogram, which we can see that is blurred, and when we have like harmonics that are too near to each other, the traditional spectrogram approach makes them overlapping. And in a reassigned spectrogram, it reassigns the time and frequency coordinates of the audio by using the phase information of the audio, and in that way we have like sharper peaks and the frequency content is more precise. So here we have a model, our model architecture. It differs from the traditional approaches in a way that it has a bipartite design. We're doing our training on both clean speech and clean speech and distorted speech. For the clean speech part does only the vocoding, we can say, and the distorted speech is used for enhancement. We have two different encoders for these two branches, and here the decoder having access to the clean speech can help the model to better converge. And as I mentioned, we derived from the voice fixer, where we used masking-based approach. It comes from the fact that human auditory system tries to mask some parts of the audio from some frequencies. So it is based on some biological information. Here, having the reassigned spectrogram helped us to improve the results of our model. The losses that we have for our training are just general adversarial training losses, discriminator losses, feature matching losses, L1 spectrogram losses, and we also have Kyle divergence loss, which tries to match the distributions of the features from the clean speech and from the distorted speech. The training process involves 1 million steps with a batch size of 4 minutes. We use an Adam optimizer with these parameters, and we did our adversarial training where both the generator and discriminator trained from the start, and the model is then fine-tuned on a specific dataset to match the audio characteristics of this dataset. For the evaluation process, the evaluation of the experiments has been done subjectively. We wrote a Streamlit program where we had a data set on which we wanted to test our results. Here we introduced the evaluator to audios from 2 different methods, and they need to choose the one that they prefer in terms of the artifacts and distortions. Here we did the evaluations mainly in our team, and then after that we discussed the results and planned the next experiments. As I said, we done the evaluation subjectively. There are evaluation metrics which are objective, but these metrics are like out of date, and they doesn't capture the full distortions and artifacts that human can listen. Here we have scale invariant signal to distortion ratio, which tries to match the structure of the clean and generated results. But yeah, this one cannot capture the artifacts that are there. So here I mentioned some paper which published this year, and this is objective and subjective evaluation of speech enhancement methods, where they where they wanted to choose the model that is the best one according to the metric, but different metrics gave different models as best one. So they concluded that these objective metrics are not enough, and subjective evaluation is required to evaluate the results. So what are our current model limitations? Artifacts and intelligibility issues from the higher reverb distorted audio. Here you can see that in a predicted spectrogram, like the harmonic structure doesn't correspond to the one that we have in a target spectrogram. So this can introduce some changes to the pitch of the audio and the natural characteristics of it. So what are our long-term goals? Our long-term goals are to work on speech enhancement using a diffusion-based approach and create a speech enhancement system that will work across diverse environments, noise types, speakers, ensuring robustness to out-of-domain data without introducing artifacts or distortions. Here we did a comparison with Adobe model, which is this is an internal evaluation where we evaluated it for 60 audios. The number of the evaluators were 15. They evaluated it for three different metrics. And here we can see that our model is mainly better, but this kind of evaluation is some kind of biased one because it's on our internal data set, and the evaluators were in our team, but we couldn't construct a big evaluation of the model.
Okay, thank you. Let's do the question. So about evaluation, could you please? So could you please go back to the evaluation? So that basically means speech quality, evaluation slide.
Which one?
Evaluation slide.
Evaluation.
Yeah, next.
This one or subjective evaluation?
Subjective. Yeah. So red, it means Adobe is better, and
no, this is just choosing two options to compare. Here we have different names for different models. This is just an example.
Yeah, but can you switch later?
You mean this one?
This one, yes.
Ah, okay.
So red, light green means Podcastle model is better. Red means Adobe model is better, and
no, this is just the percent. We evaluated 60 audios, and this is the percent of the audios that where the Adobe model were better. Like in 60% it was better. In 16% of the audios, it was better in speech quality.
Ah, okay. Yes. Okay. Thank you.
So you can listen to noisy examples. I collected several examples to show you different issues.
Hello everyone. Today I want to talk to you about how you can improve your pronunciation with just some simple tricks. Hello everyone. Today I want to talk to you about how you can improve your pronunciation with just some simple tricks.
Here you noticed it.
want to test a man's character, give him power. Good morning. It's February 28th. Quote comes from Abraham Lincoln. Nearly all men can stand adversity, but if you want to test a man's character, give him power.
This noise is artificial or is natural?
Which noise?
The noise on the left one is artificially added or?
No, it's real live recording.
Cool.
There's a lot of growth that's going to happen, and we all want to make sure we're growing the industry in the right way. So I think we all kind of have to step up and make sure that this stuff is handled.
And the fourth one is an Indian accent. It can make it more beautiful.
I am what you call an indie podcaster. If I run out of money, there's nobody backing Crazy Fitness Guy. How you can support Crazy Fitness Guy is becoming a premium subscriber. I am what you call an indie podcaster. If I run out of money, there's nobody backing Crazy Fitness Guy. How you can support Crazy Fitness Guy is becoming a premium subscriber.
So that's it. Any questions?
Thank you very much. I wanted to ask you about aspects of your pipeline which significantly improve the results. I saw that you use different data augmentations, yes, like noise, reverb, delay, and so on. I saw a very interesting architecture structure, and I saw that you applied different interesting losses, actually, like adversarial loss and so on. Could you please say which from all these pipeline features improve the results mostly? It's very interesting. Maybe one loss or one application is quite interesting.
I cannot say like one thing that improved the results significantly because the experiments were done like step by step, and there were changes like that. The result has improved like gradually. There was no any change that impacted significantly, but the reassigned spectrogram part was a great one.
More questions?
Yeah. I'm interested, like, how big is the model? Can it be run on device or on live data?
The model is about 300 million parameters, and I can't like really answer this question. It can work on device, like on the phones, but I can say you about the RTF of the model. It can process like 1 hour audio in 5 minutes on our system.
Thank you.
Thank you so much for the presentation. And I want to ask about the speed of the model. For example, it takes how much seconds, can it run real life?
RTF?
Yes.
I thought it can process 1 hour speech in 5 minutes.
5 minutes? Okay.
With GPUs.
What?
With GPUs.
Yeah.
Can it be used on live streams?
What?
Can it be used on live streams?
Yes, it can, but we haven't considered that yet.
But it's not streaming, right? In a way, it's designed that way.
It can work in real time, but we haven't approached this yet.
Put one more GPU with you. And cool. This is a good work. Yeah, so let's thank the speaker again.
Thank you.